Hello guys, this is the third part of the grammars. Let's get started. So far we have learned that we can derive a string from a grammar. We know what the concepts of derivation is. In this section we want to find a discipline for it. Let's assume we are creating an algorithm for derivation. And for example, look at this grammar. We have S is defined as A, B, and we have some other production rules for A and B. Now, to derive a string, we need to substitute A and B of the production rule number one with these guys. But the question is, in what order? Can we just randomly substitute sometimes, for example, A, sometimes from B? Is this the case? Or we need a discipline and pick a specific order? Definitely you would say, hey, discipline. For creating an algorithm, we need a discipline. So we just cross off this guy and focus on this. So we need a discipline. So let me explain through an example what kind of discipline we have. Derive a string AAB. So the target is AAB. And here is the grammar. But for this specific purpose, let me separate all of these production rules in different production rules because I want to refer and address the production rule number. So something like this. Now substitute the leftmost variable first. So this is our first discipline. We substitute the leftmost variable first. What does it mean? Let's do it in practice and see what's the meaning of leftmost substitution. So the goal is AAB, and look at this. The starting point is S, so we always need to start from the S. So S derives AB. Based on this discipline, leftmost variable should be substituted. So we focus on A. All right, look at these two A's. Either we can substitute with lambda or we can substitute with AAA. We look at the target. Oh, we need an AA. So definitely we will be using this guy. So number 2. And for this one, we use number 1. So instead of this A, we will have A, and B. Okay. Again, leftmost variable first dictates that we need to work on this A. All right, so since we already have our AA, how about we substitute this guy as lambda? Yeah, that's a good idea. So it will be AA lambda and B. So which one we used? Rule number 3. Now the leftmost variable will be this B and this lambda will be vanished. Okay, so since we need a B here, we need to substitute with this guy. So it will be A, B, B. Which one we use? Number 4. And we already have AAB, so we substitute this B with lambda and we will get AAB. So we use number 5. So this way we use the leftmost variable first technique or discipline to derive a string. Do we have other approaches? Yeah, I am sure that you guessed that we can have rightmost variable first. Yeah, all right. So let's use this discipline now. Again, we start with S, defined AB. So we used rule number 1. So the rightmost, we need to work on this guy. Since we need a B, definitely we will use this guy 4, and it will be A, B, B. And we don't need any more B. This guy rightmost will be replaced by number 5, lambda. Now what? just we have one variable here. We will go with this one. Number 2 will be A, B, and we already have our AAB. So we substitute with number 3 and we get AAB. As you see, both disciplines yield to the same result. But at least we have a discipline right now for derivation. So here the official definition of the leftmost and rightmost derivation. A derivation is called leftmost if in each step the leftmost variable in the sentential form is substituted. And we have this a similar definition for rightmost derivation. But the point is the default is leftmost. So if we don't mention any discipline, you need to use the leftmost. All right, so I put some exercises for you guys. In this section, we're going to introduce parsing. Parsing is a very important topic in computer science. There are many theorems, algorithms, and lots of research is still in progress. In this lecture, we gave you only a big picture about it. Consider this section as a short introduction about parsing. So for more information, you need to take compiler course. Let's start with a good reason why parser is so important and why should we learn it. All right, look at this Java code. It looks like a simple if statement. Now the question is how Java compiler figure that this is a valid statement? Very good question, right? When you are writing this code, if you make any mistake, the code won't be compiled. Now the question is how Java compiler figured it out. Yeah, look to answer this question. Let me remove all of the white spaces. Yeah, the result is a string. So I removed all of these white spaces, I mean the spaces, the tabs, and the new lines, right? The new lines here, and I just get this. This is just a string. Do you agree that? So based on our knowledge, yeah, this is a string like any other strings that we have seen so far. Yeah, the strings we have learned and we have seen so far, for example, A, B, B, yeah, it was meaningless, but this one, yeah, it's just so familiar. All right, let me repeat my question. How does Java compiler figure that this is a valid statement? Do you agree that if I combine all of my knowledge so far, if I create a grammar for this if statement, and then if I can derive this string from this grammar, then I can say that, hey, this string is well formed that can be considered as equivalent to the valid. So valid is equivalent to well formed. All right, so we mixed all of our knowledge and now we know what we are looking for. So I talked about creating a grammar just for giving you a taste of how this grammar looks like. Let me try to create a simple grammar for this if statement. But Java grammar for this if statement is a very big and very complicated. Since this is just a taste, I need to simplify this as much as I can. For example, the identifier for this condition and this statement is just x and y. Arithmetic operation, just multiplication and addition. Conditional operator, just these three guys, greater than, less than, or equal. And only we have one condition. So even though in Java we can have several conditions and combining them with and or, yeah, and here we just have one condition, something like this. x less than 5, 5 less than x, and so forth. And for the statement part, this part, we can have only one statement, and the statements look like this. So it is one identifier on the left side, and on the right side, we will have some multiplication terms like this, or a digit like this, or digit, or let's say some just identifier like this. Okay, so these are the requirements for our simplified grammar for if statement. I put all of these requirements here for our reference. Okay, so look at this if statement. What do we need here? So S is defined as, this part is always if, and these parentheses are always the same thing. So they are actually terminals. So I would say S is defined as if, parenthesis, but the condition and the statement can change. Therefore, condition and statement, both of them are variables. Let me define C for the condition, and for the statement, since S is already being used, let's use it as T, for example. So this is the if statement. Okay, so now we need to work on the C and T because the rest of them are just terminals, right? Okay, so what is the C? The condition, look at this condition. You see here, the condition, we have some identifiers, some digits, and some operators. All right. Yeah, we have these three things in all of them. So let's first define the digits. So digit or D, yeah, we would need this D later, and we will work on the C and T, in a few minutes. So D is defined as, the digit can be 0 or 1 or 2, and we can continue until 9. What else? We can have, let's say, 55 or 57 or something like that. How can I create double digit? Do you agree that if I put DD here, I can create double digit or more? Let's say, for example, 571. So how can I make that? I would say D goes to DD, and then I would substitute 5 here, and this D again with another DD derives with 5, 7, 1. So 7, 1, we are done. You see, we can create with this DD several digits here. All right. So this is the D. What else we need? Identifier. All right. So identifier goes to, let's define it as I, as X or Y. And what else we need are these operators. So let's call it O is defined as, we have three symbols for identifier, either greater than or less than or equal. Cool. What else? Now I think we are ready to introduce the conditions because we already have all of these three elements. So the condition either is identifier, operator, identifier, something like x greater than y, something like that. Or it would be identifier, operator, digit, or digit, operator, identifier, or digit, operator, digit. Yeah? So we can have something like, for example, 5 greater than, let's say, 15, something like that. Okay, so we are done with the condition. Now let's focus on the T. What is the T looks like? T is defined as, on the left side, we always have an identifier. So it would be I equal to What do we have on the right side? On the right side, if you look at this carefully, we will have something like this. It's a multiplication term, or we can have like something like this as a digit or an identifier like this. So I would say we have an identifier on the left side equal to, and we have an expression on the right side and also a semicolon here. Now let's work on that expression. So this expression, as I said, it can be some multiplication term, something like this. So not bad if I have the multiplication term first. So I would say m as multiplication term. It can be an identifier multiplied by a digit, or it can be a digit multiplied by I, or identifier, or it can be two digits multiplying with each other, or we can have two multipliers, m, I mean two of these multiply with each other, or it can be either an one identifier like this one, or it can be just a digit d. So I try to simplify these multiplier terms here, and we have all of the possibilities that it can happen here. Now we are ready to define this e. This e can be the right side of this guy. Okay, so if you look at this, it is either m, so e is defined as either it is just one m, one of these guys, or it can be 1m plus another expression. Okay, so with this definition for the e, we can create any combination of these guys. So this is the grammar for our simplified version of the Java if statement. And here I put all of them here for your reference. But at the end, I would like to tell you that this grammar is neither efficient nor practical. If you use this grammar, it would be a disaster when you want to compile a code. How come? Yeah, that's a good question. You need to wait until I am talking about the complexity. Okay? But it will give you an idea that how a grammar for compiler can be written. So I put some exercises for you guys. Try to derive this to if statement. Okay, now let's get back to our main question. We were talking about the parsing, yeah? And all of these stuff that I just mentioned was about the motivation. Okay, so what do we need for parsing? First of all, we would need a grammar. Second, we need a software that we call it parser, whose job is to get a string like that if statement that we have seen so far, and it gives us a parse tree. So parser's job is to convert a flat string to a data structure, because flat string is useless. We need to convert a string to a data structure that here is just the parse tree, and we will be talking about in a few minutes, to be able to use it for compiler stuff. And here I need to explain that, hey, the real compiler and the parsers is more complicated than whatever I am saying here, and you really need to take the compiler course for more information. We mentioned parse tree in the previous section. Let's see what is parse tree first before going further. So I'm gonna explain it through an example, and I start with the simplest one. How can we construct a parse tree for only one production rule? So let's assume this is our production rule. It would be very easy. So we use this left-hand side as a parent like this, and we put all of the right-hand side elements or symbols and variables as children. For example, this A, we have a child here A, another for B, A, the variable B, and terminal C. Please note that even though this is a tree, but the order of the children matters because we are talking about the strings, and a string, which is a sequence of symbols, the order of the symbols matters. Let me give you another example. So we have this grammar, and our job is to create a parse tree for this string. Needless to say that every string has its own parse tree. So this parse tree is only for this string. We have one starting variable here, so we have to start with the S. So one child will be A, one child will be B. Now we keep an eye in our target, which is A, B. We use this production rule. So A goes to A, and the variable A. And then, since we are already done with the AA, this A goes to lambda. We are using this guy. How about this B? This B, we will be using this guy. It will be B and the terminal B, and this B goes to lambda. And if you look at these children here, you will see that our parse tree created A lambda lambda B, which is equal to B. So this is the parse tree for B. All right, I put some exercises for you guys. In this section, we are going to talk about parsing algorithms, but since these algorithms are beyond the scope of this course, we just give you a taste about them. So we are not going to talk about a specific algorithm. We will just mention a very general purpose one. Let's see what we got here. We are going to explain a top-down algorithm that is called exhaustive search or brute force. In general, we can create an exhaustive or brute force algorithm for every problem that is computable. They are not usually efficient, but at least they can solve the problem. So in this case, they check all possibilities to derive a string. I'm going to talk about that and explain that through an example. So here is our grammar. The target is deriving this string A, B. S is defined as SS, ASB, BSA, and lambda. Let me give you a big picture what procedure we are gonna follow. So we have this string here, we have the grammar here, and we are gonna apply an algorithm for this parser, and this parser is gonna give us the derivation sequence. When we get this derivation sequence, creating a parse tree, as we will see in a few minutes, it will be very easy. All right, let's get started. Okay, so we will have several iterations. In iteration one, we start from here. So S is gonna derive SS. How many possibility we have? All of them are S. So S can derive ASB, and S can derive BSA, and S can derive lambda. Just remember that we are gonna use an exhaustive search parsing or brute force, and this kind of algorithm check all possibilities. Okay, so for the iteration one, we have four possibilities. It's time to prune some of them that does not lead to the goal. Can this SS lead to AABB? Yes. How about this one? Yes. How about this one? No. Because this guy starts with B and we will never get AABB from this guy. How about this one? This is already terminated. So do you agree that these two should be cross off? We will be using pruning term here to cross off those that really do not lead to the goal. So the result of the iteration 1 will be these two. Let's start the iteration number 2. So here is the conclusion of iteration 1. Now we need to use the leftmost derivation, which was the default one. You remember that? And substitute the leftmost variable with something. With what? We have four possibilities. So do you agree that each of these derivation we need to substitute the leftmost s with four possibilities? Yes, of course. We substitute this s with ss. We can substitute this s with ASB. This guy I'm talking about. We can substitute this s with BSA and so forth. So we will have four possibilities here. So this is the result of substitution for the first one. How about the second one? Exactly the same thing. Okay, now it's time to prune which one does not lead to our goal. So SSS is fine, ASBS is fine, but not this one, right? We can cross off this one. This is okay. This is okay. This is okay. This is never, and this is already terminated. So, do you agree that we need to prune all of this stuff? All right. We can continue this and you see how fast it is growing. So each of these will have four possibilities and I need to substitute the leftmost s to four of these possibilities. Yeah, since you got the idea, let's have some cheating and just pick one of them that is, promising result, and that would be this guy that already we have these AA and BB, which is our goal here, right? Okay, so we just substitute this S with four possibilities, and the last one, the S is actually is substituted with lambda, and we got this AA, BB, which is our target. Okay, it means that this algorithm will solve the problem even though it is inefficient, and it gives us the derivation sequence. So it is saying that, hey, S should derive ASB, and then this S should be substituted with ASB, another ASB, and then we need to substitute lambda for this s. So this derivation sequence is actually the key for creating the parse tree. Let's see how can we do that. S goes to A, S, B. We are here. And then this S goes to another A, S, B. We are here. And now we know that I just removed that lambda. This goes to lambda. And this will be our target string. All right, now let me talk a little bit about the complexity of this algorithm. Actually, it's horrible algorithm. Yeah, it's so inefficient and its complexity, we can prove that its complexity is something like this. big O of the size of the production rules, and this W is the size of the string. You see how fast it can grow when the string is bigger and bigger. So it's an exponential algorithm, right? And the second point I want to mention here, if we really don't put some controls in our code for the parser, then in some cases it never stops. As an example, just try this string and follow the same thing that we did, and you will see that it never stops. All right, so I'll get back to this problem and this efficiency later when I am talking about the complexity. Let me give you some good news. We have a theorem. If we have a context-free grammar, then there exists an algorithm that parses any W belongs to the language with this complexity, which is a polynomial complexity, which is really a huge improvement. You just compare it with this, which is an exponential. Yeah, we get back to this later. The second good news is if we use the S grammar, then the complexity would be big O of size of W, that is equivalent to big O of N. So N is the size of the W or a string, which is huge improvement compared to this guy. What is this S grammar that is magic for us for parsing? Yeah, that's a good question. So let's see what is S grammar here. S grammar, first of all, it is a context-free grammar, but it has two extra conditions. So by the way, S grammar is abbreviation for simple grammar. Okay, so what are those two conditions? The first condition is all of the production rules are of the form this. What is this? Let's dig a little bit more into it and see what it is saying here. So we have X here, that X belongs to alphabet. So we have one terminal here, one and only one terminal here. And what is this V here? V belongs to V star. And V star means zero or more concatenation of the v's or variables. So in fact, we have one terminal on the right side, and we can have any number of variables, right? But one terminal here. So this is the condition number one. How about the condition number two? The condition number two is very amazing. It is saying that this pair should be unique. What is this pair? This guy, this variable, whatever it is, and this terminal. So this combination should be unique through all of the production rules. What does it mean? Yeah, let me take an example to clarify. So the question is this an S grammar? Okay, so to verify whether it is S grammar or not, first of all, it should be context-free. What is context-free? On the left side, we need to have one variable that we have here. Here we have S, A, B, B, yeah. On the right side, we can have any combination of the terminals and variables, all right? Now we need to test two conditions. First condition, we need to have only one terminal and any combination of variable. Yes, this is correct. How about this? One terminal, any combination of variables? Yes. One terminal, any combination of the variables? Yes. And one terminal, yeah, zero combination of variables is okay too. So the condition one is okay. What is condition number two? Condition number two, it is saying that S and A should be unique S and A. Do we have any S and A here? No. S and A, this combination is unique, okay? How about the next one? A and B. There shouldn't be any A and B on the rest of the production rules. Yeah, A and B is unique too. How about B and B? Yeah, B and B is unique. And how about B and C? Yeah, so you see, all of them are unique, these combinations. So the second condition is okay too. So definitely this is an S grammar. And please note that in S grammar, we don't have lambda here. Just to review one more time the definition of the S grammar, you will see that lambda is not allowed in S grammar. Another example, is this an S grammar? Okay, so very quickly we can see that it is a context-free grammar, yes. So the first condition, S and B, yeah, so we have one terminal here and any combination of the variables, one terminal, any combination, one terminal, one terminal, any combination. Condition number one is okay. How about condition number two? So S and B should be unique. S and B, S and B, S and B. Yes, S and B is unique. How about S and A? S and A, we have one here, one here. So it is not okay. So this is definitely not an S grammar. Okay, now why S grammar is important and how useful it is. Let's derive a string like this, A, B, C, C, from this grammar. All right. We have A here. Which of these guys do you think that we should start? We can start with this, but we keep an eye on the target and we see it starts with A. So definitely these two are not good. This one is good. And since S and A is unique, it means that whatever we have here, only one production rule has that S and A. So absolutely uniquely, we need to start with this. Okay? So S derives a S. Now look at this. We need a B. So these S and B should be unique too, right? So we just need to find that S and B here. So we substitute this S with BSS. Now what? We need C. So S and C is unique again. So we have to use the number 3. The last one is C. Again, we need to use this guy. So you see, in one pass, we can derive any string if we have S grammar. Now let me give you some notes. We still are using the exhaustive search parsing. We didn't change our algorithm, but the format of the grammar is in such a way that in one pass, in one iteration, we can reach to the goal. Another note here is that each string has a unique derivation. In this section, we want to talk about an issue that can happen in some grammars, and actually that's not a good thing. Okay, let me explain here. So we have learned that the parsers produce parse tree for every strings of a language. But the point is, in some cases, for one string, we can have more than one parse tree, and that's not good. So it means that the parse tree for some of the strings are not unique. So what is the consequence? Yeah, let me first of all take an example that this might happen, and then I take another example show you that what would be the problem in practice. This is our grammar and this is our goal. Based on which production rule we start, we might have two different parse tree. For example, if we start with the first one, this is the parse tree, yeah, S, A, S, B, and then since we want to reach this goal, we substitute this S with another ASB and finally lambda. So this is one parse tree. But for the same string, we might start with the second production rule. Okay, so S goes to SS, and the leftmost S goes to lambda, and this S goes to ASB, and this S again with another ASB, and finally lambda. So as you see, we will have the same AAA BB string. All right. So this example shows that it is possible we can have more than one parse tree for one string. Now let me take another example and show you that what is the consequence. Let's say this is a grammar for computing mathematical expressions like this. Based on the priorities, we know that this operation should happen first, so it will be 10, and 10 plus 3, the result should be 13. But since we can have for this particular expression more than one parse tree, yeah, we will get different results. Look at this grammar. The starting variable is e, and we can start with this one, or even this one. Yeah, let's start with the first one and see what would happen. So e goes to e multiplied by another e. So we are using the number 1. And then we keep an eye on the target, which is this. Then based on that, we substitute this e with e plus e. And then each e goes to the right digits. Okay, so up to here, we have 3 plus 5 here. Okay, how about the right side? On the right, we have E and it goes to 2. Okay, so if this is the case, and if this is the parse tree, and let's say that the compiler wants to use this parse tree and calculate this expression, then how it calculates? Okay, so 3 goes here and 5 goes here, and then this operation happens, the result goes here, and this 2 goes here, and then this operation will happen, and we will get 16. And we know that the result should be 13, not 16. So what's happening here? Because the plus is calculating first, and that's wrong, because multiplication has higher priority. Okay? All right, so this is not a good parse tree. If we start with this guy, then it will be the right one. How? Yeah, look at this. So we started with number 2. In fact, we need to start with the operation that has lower precedence. Okay, because all of the operations on the children happens first, so we need to create the parse tree in such a way that those operations that have higher precedence goes to the down to the close to the I mean the leaves. Okay, so here, yeah, it will go 5 here and then 2 here, and then this operation will happen and we get 10 here. The same thing, 3 goes here, and then this operation gives us 13. That is the right answer. So yes, this is the good one. So let's see both of them side by side, and this is the one that we really desire to have. Okay, based on this experience, what is the ambiguity in grammars? The definition of ambiguity is like this. A grammar is said to be ambiguous if there exists at least one string that has two or more different parse trees. Okay, so that's the point. If at least one string in a language that a grammar can produce has two or more different parse trees, then we would say the entire grammar is ambiguous. All right. In some cases, we may convert an ambiguous grammar to non-ambiguous. Actually, it has some techniques that is beyond of this course. And here is the way that we can change the given grammar in such a way that it won't be ambiguous anymore. Okay? As I said, we need to have the operations that has lowest priority at the beginning. So we change this way. Okay? First of all, we make sure that we have one starting point and we change that this way. So E is defined as E plus M or M. So what is M? M is actually multiplication terms. And we define multiplication terms as this. It is either M multiplied by a digit or a digit. Okay? And digits, we don't change the digit as it was. Okay, so based on this, if we construct a parse tree for the same mathematical expression, we just have one way to go that way. So the starting is always this guy, and as you see, the addition is on the top and the multiplication is closer to the leaves. Okay, so this 5 goes here and this 2 goes here and this operation happens first and at the end this operation. So this is the right answer for this. Okay, we are done with the parser. Before finishing this lecture, I would like to introduce two open questions we have. The first one is we have a context-free grammar G, and we are looking for an algorithm whose job is to find out whether this context-free grammar is ambiguous or not. Yeah, as of this moment, we couldn't find any algorithm for this problem. The second open question is we have two context-free grammars and we are looking for an algorithm to tell us whether these two are equivalent or inequivalent. Again, as of this moment, such an algorithm does not exist. I am gonna stop here. See you guys in the next video.